Be careful. Be careful. Be careful. All right. Last thing, 4.6, matrices and transformations. In geometry, you would have dealt with transformations, right? Rings the bell? Ding-a-ling. Okay, transformations. Basically, a transformation is a general term used for the four ways to manipulate change, right? A shape or figure. Anybody remember any of the four ways of manipulating or changing a figure? Abigail, give me one. Reflecting is one, yes. A reflection. Great. Maybe that'll jog your memory. That's one of them, to reflect. Any others? Come on, think. Josh? Okay, I think you might mean translation. So that is a second one. Translation. So we got translation, reflection. What else? 8. Dilation is another one. And the last one is the last one is, all right, let me show you all four of them here if I can get rid of this thing. And the last one is rotation. You might want to write those in like right after the word figure. Just write the four of them. We're going to talk about all four as we go, but it'd probably be good right up there to write translation, reflection, rotation, dilation. Translation, reflection, rotation, dilation. Am, is, are, was, were, being, but no, that's something else. Sorry. All right. Translation, reflection, rotation, dilation. Brings back fond memories, warm memories of geometry. Oh, yes. Awesome. All right, we'll talk about each of these in just a little bit. Translation, you're moving an object. It's the same object. It's congruent object. Looks just the same. You're simply moving it to another location. Translation. To be translated. On the Mount of Transfiguration, there was a translation. All right, anyhow. Reflection. You'd still have a congruent shape. Well, same size and shape. Yeah, I guess technically it's congruent. But you're reflected, and the reflection is going to usually be about some kind of a line. The one there is reflected about the y-axis. You can reflect it about the x-axis. You can reflect it about any kind of an angle, and we'll look at those. Third one, rotation. So now you're going to rotate an object. Normally the rotation is counterclockwise, just like your angles would be, right? When you guys did geometry, if you were to draw in standard position a 100-degree angle, you would put the initial ray along the positive x-axis, right? And you would put, I'm speaking Greek, I can see. You would put, here I'll go right on rotation. You would put the initial ray along the positive x-axis, and then you would open up counterclockwise 100 degrees, right? And get a 100-degree angle, because that's standard form. Angles open, yeah, it's a little bigger, no big deal. Angles open counterclockwise. And that's why this is quadrant 1, and this is quad 2, etc., because of the way the angle's open. The rotation angle is going to be exactly the same. If you use any type of drawing program that allows you to rotate an object, it's going to be the same thing. If you stick in rotate 90 degrees, it's going to rotate it counterclockwise 90 degrees. If you want the object to rotate clockwise, you got to stick in, negative 90. But rotation, and then the last one is the dilation. Your pupils dilate depending upon sunlight and darkness, right? An enlargement or a reduction is a dilation. So enlarge an object or to reduce it would be a dilation. All right, so Now we need to do all this with matrices. And again, if you were programming, it would be with arrays, and there are commands and such like that. But basically, we'll look at the matrix math behind all that. All right, let me get rid of this. Okay, so some more geometry that hopefully you guys remember. The original shape of the object is called the pre-image. So the original is the pre-image. And the final shape and or position of the object, depending upon how you transform it, is called the image. And again, you guys would have gone through all this in geometry. Those aspects. You got a pre-image and an image. Why isn't an image and a post-image? I don't know, because somebody wanted the final product to be the image, so that had to make the beginning product the pre-image. Don't ask me why. I'm sure there's some reason. I know not, though. All right, A. So let's do a translation. A translation. We want to take that object and we want to move it to another location. Okay, so let's go ahead and make up a matrix, and we're going to make up a 2x4, and the P stands for the pre-image, and the I stands for the image. Okay, and just to make life easy, let's go point A, then point B, point C, and point D. We've done this before, right? And we're just going to do the coordinates of the shape. And I'm going to use red for my top row because those are all the x-coordinates. And so the x-coordinate of point A is a -4, right? And the x-coordinate of point B is a -3. And the x-coordinate of point C is a -2. And the x-coordinate of point D is a -1. So again, I'm just looking at the blue pre-image, and I'm simply writing the x-coordinates, and then underneath the y-coordinates. So what do we got? 3, 5, 5, 3. 3, yeah, 5, 5, 3. Okay, nothing earth-shattering. So then just go ahead and go through now for the pre-image and write the resulting matrix of the coordinates for the pre-image, or for the image, I'm sorry. Two, three, four, five, right? And what? 1, 3, 3, 1. 1, 3, 3, 1. So what happened to our image? And hopefully you look at it and say, so how is this thing translated? Somebody describe the translation. Luke? Yeah, so we're right 6, and we are down 2. All right, we translated the object to the right 6, and we went down 2. Looking at the matrix of the pre-image and looking at the matrix of the image, does going to the right 6 and down 2 make any sense looking at the values in the two matrices? Do you see a connection? Do you see how you get from the pre-image to the image? All right, so look and see if you can find the pattern. And just like we did slopes, right? Math is nice because it's consistent in its thoughts and processes and applications. When you're talking about the x coordinate, to the right is positive, to the left is negative. So if you simply add 6 to every x coordinate, don't you get the x coordinates of the image? And again, on the y-axis, up is positive, down is negative. So if you add a -2 to every y-coordinate, don't you get the values of the image? And you do. So it's just simply this. So that then can hopefully allow us to make this conclusion. The matrix operation to translate an object is, class, say it if you know it, addition. It's just matrix addition. So you're doing programming and you have an array, which is basically a matrix to represent an object, and you want to move that object somewhere else on the screen. All you do is create a matrix that gives you the movement you want. If you want to go right 6 and down 2, you then simply tell the program to add the matrix of the object with the matrix you created to move it, and it's moved. And that's how things work. Okay, pretty simplistic. Hopefully that's not extremely confusing, though it is new. So we're simply going to translate with addition. So what do we got here for the example? Make a matrix equation that translates triangle JKL 5 units to the right and 4 units down, and then graph the image. Okay, so we've got on the left there the matrix for the pre-image, right? So let's check here. -2, 0, 1, that looks good. And 2, 4, 2, that looks good. Okay, so again, I want to take this object, I want to move it 5 units right, I want to move it 4 units down. Now, you guys haven't done this before. So what do I stick right there in that circle? Say it if you know it. Yeah, that's just a plus sign, right? Because we're doing matrix addition. And if you have no clue how to get there, and you might not, you might say, well, I don't know what to make this matrix addition part look like. You can write what you know the object's matrix will end up being, the matrix of the image. Because you can take that shape, and you should be able to move that shape 5 units right and 4 units down and draw it. So you can work backwards if you want, or if you think you know what's going on, go ahead and write this matrix right here, that when you add it to the pre-image matrix will then end up giving you the translation of that object 5 units right and 4 units down. Okay, so you can work forwards or backwards. I'll give you just a minute and then I'll explain it. Okay, so hopefully you're moving along that process. Basically the reality is if we got to move it 5 right, each of these values are simply 5. That's all it is. And if we've got to move it 4 down, then each of these are -4. We'll end up with the resulting matrix of 3, 5, 6. And the bottom row would be -2, 0, -2. And if I were to graph that, 3, -2, 5, 0, and 6, -2. There's my image, and what is this? J prime, K prime, L prime. How far did the K point move? The K point moved 5 right and 4 down, right? How much did the J point move? 5 right and 4 down. How much did the L point move? 5 right and 4 down, right? So it's not hard once you understand. I mean, it's pretty simplistic. You want to move it 5 right and 4 down, make up the matrix, 5, 5, 5, -4, -4, -4, add them up, voila, you are there. Any questions on translation? So obviously this is a key thing to remember, that you translate it with addition, right? Matrix addition is going to translate the object. Let's go to our next one. All right, so that was translation. Next, let's do reflection. Movement of an object across a line of symmetry. Movement of an object across a line of symmetry. So let's do the same thing here. Let's go ahead and write the matrix for the pre-image and then the matrix for the image. So again, I'm going to do all the x coordinates first. I'm going to go in order, right? A, B, C, D. So what do you got? 2, 3, 5, 5. Hopefully you're just not writing 2, 3, 5, 5, but you're looking at the pre-image, the blue one. And you say, yeah, the A is a 2 and the B is a 3 and the C is a 5 and the D is a 5 for x coordinates, right? And then the bottom row is going to be their y coordinates. Point A, y coordinate of 1. Point B, y coordinate of 3. C, 3. D, 1. So 1, 3, 3, 1. And then just look at the image and go ahead and write the x coordinates across the top. Again, be careful though, right? You still got to go A, B, C, D, right? A prime, B prime, C prime, D prime. So what do you get? 2, 3, 5, 5. No change, right? Let me pause right there before we go any further. All right, our x coordinates didn't change. Will that be the case for every reflection? Will that be the case for every reflection? And the answer is no. It is if your line of symmetry is the x-axis. But you can reflect it across the y-axis. You can reflect it across an angle. So there's a multitude of possibilities. You can, if you want to, you don't even have to use the x-axis as your line of symmetry. I mean, what if you come down here and make like that the line of symmetry? Now the red one's going to be that much further, right? The blue one is what? 1, 2, 3, 3 above that line. And the red one would start 3 below that line, right? So there's all kinds of possibilities. So don't just assume, okay, it's a reflection, the x-coordinates stay the same. No, for this one, because we're reflecting about the x-axis. All right, go through and what are our y's? -1, -3, -3, -1. -1, -3, -3, -1. All right, so the matrix operation to reflect an object is left. Any thought? You look below, multiplication. Left multiplication. Remember when we were solving the matrix equation yesterday? And Abigail asked, when you multiply both sides by the inverse matrix, can it go in the back or in the front? Does it matter? And it mattered, right? It had to be in the front. Because again, if it's not, then the matrices won't be able to multiply and you get a different value anyhow because of the cross down pattern. So left multiplication means that what you multiply by has to end up in the left. Go ahead and do that and you'll reflect it. And if you look down your sheet, you can see now we've got a bunch of possibilities. So number one is let's reflect it about the y-axis. What do you multiply the matrix by? By a -1, 0 top row, 0, 1 bottom row. That will reflect the object across the y-axis, no matter where it's located. And it doesn't matter if the pre-image is in quadrant 1 or 2 on the right-hand side of the y-axis, or the pre-image is in quadrant 3 or 4, the left-hand side of the y-axis. Multiplying by a negative 1, 0, 0, 1 will reflect it across that axis. It's magic. I don't know if you use drawing programs and if you reflect something, for me, I have a reflect command that I can go up and choose reflect the object and it'll reflect it. Normally, I think the default is to reflect across the y-axis. But that's what's going on. Multiply by that matrix. Go ahead and do it. You're going to reflect it. Second scenario, we just did that, right? Multiply across the y-axis. It's to multiply by a 1, 0, 0, negative 1. So let's go back up here. So remember, it's left multiplication. So what if we multiply this thing by 1, 0, 0, negative 1? Right? So you can just watch if you want, or you can write it if you want, but let's see where we end up. So we're going across and down, right? Remember the pattern? So right now I'm going across the top row. Right? So 1 times 2 is 2. 0 times 1 is 0, and the top coordinate is 2. I'm going to keep going across now to the second column, right? Now I'm going to do the second column. 1 times 3 is 3. 0 times 3 is 0. You get a 3. Third column. 1 times 5 is 5. 0 times 3 is 0. You get a 5. Fourth column. 1 times 5 is 5. 0 times 1 is 0. You get a 5. Okay, so far we're good. It matches what we end up with, 2, 3, 5, 5. Now I'm going to go across and down. So now I'm going across the bottom row, down the first column, right? 0 times 2 is 0. Negative 1 times 1 is a negative 1. Good, that one works. Second column. 0 times 3 is 0. Negative 1 times 3, negative 3. Oh, we're still good to go. Third column, you get a negative 3. Fourth column, 0 times 5 is 0. Negative 1 times 1 is a negative 1. And lo and behold, right, we got that matrix. And, of course you would if the math is right and if we're doing it right. Okay, so how do you reflect about the y-axis, the x-axis? Then you've got that matrix. If you looked down the road, and you probably have, how do you multiply about a 45-degree angle? Hopefully you agree that's what this is. This is a 45-degree angle. Geometry, a tangent of, but you know the value of the tangent for a 45-degree angle? Tangent of 1 is a 45-degree angle. All right, how would you do that? So the matrix, top row, 0, 1, bottom row, 1, 0. Now you'll be across that 45-degree angled line, no matter where the object is. And I'm showing you the easier ones to show, but it doesn't matter. Take your original matrix and multiply it left multiplication, 0, 1, 1, 0. And then what if you have a negative 45-degree angle, which is the same as a 135-degree angle? Geometry, 135 clockwise, negative 45, or 135 counterclockwise, negative 45 clockwise, right? And what's the matrix there? 0, negative 1, negative 1, 0. Use those and you'll be able to translate all the objects. If I ask you on a quiz or test to reflect, I'll give you the matrix, because in my mind, if I make you memorize those 4 matrices, you'll know them for the test and you'll forget them, after that. I mean, who's going to remember that a month later without using it? Maybe one person in here, maybe. Okay, because you got to have that good of a memory. So I'm not going to make you memorize those 4. I'll give it to you and ask you then to reflect it, okay? So you don't have to memorize those 4, because it gets tricky, because we get a bunch more when we do rotation. So I'm not going to make you memorize them, but we'll have to learn how to use them. And do I have time to do the last thing? Yeah, let's at least start it. So we're going to, first off, let's write a matrix for the object. Okay, that should be easy now. And when you write, let's stick it here though, right? Because we got to left multiply. So write a matrix equation that reflects triangle NOP about the x-axis, reflected about the x-axis, and then graph the image. So what do we got? A 1, 3, 4 for the x-coordinates. Just looking at the shape, right? Just reading right off the graph. Say the y-coordinates if you know them. Go ahead, go. All right, so 2, 4, 2. And what matrix are we going to left multiply by? So again, we're reflecting about the... Why did I do x-axis? We already... All right, let's not do x-axis. We already did one of those. Let's go with the y-axis. Why not? Yeah, let's reflect about the y-axis. Do something we haven't done. All right, so you're going to multiply what? Top row, -1, 0. Bottom row, 0, 1. Top row, -1, 0. Bottom row, 0, 1. By the way, if you haven't caught on, the red simply is when you get away from the normal pattern, but it's not a big deal. Again, it's a little bit obtuse of a pattern. Okay, so now all you got to do is multiply across and down, across and down. Bell's going to ring, so we'll pick up here, mañana.